Hello everybody. In this video I want to help you understand circular motion. This is the kind of motion that you would have, for example, if you were to drive at say 60 miles an hour constant speed in the 610 loop in Houston. So you're moving along a trajectory that is a circle and you're doing so with constant speed. To understand this, let me show you a little video of a turntable, this ancient technology that was used long time ago to record and reproduce music. So you're looking at one of those here, and we have marked 2 points, one yellow, one purple. Let's focus on the purple one for now, that are going to be spinning around as the turntable is turned on. So this is an example of circular motion. The pink dot is moving with constant speed, but it's moving around, not in a straight line. So the question that we want to discuss here is whether there is an acceleration, whether an object moving in circular motion, uniform circular motion, meaning with constant speed, moving in a circle, whether an object moving in such way does have an acceleration or not. So to tackle this question, what I want to do is mark the location, record the location of the pink dot at a certain intervals of time. So every, say, 0.1 seconds, we're going to record the location of the pink dot as the turntable spins. So if we do that, this is what we get, a pattern of points. There's 10 of them here. So let's label those points from 1 to 10. And let's draw the position vector corresponding to each one of those points. So there we have 10 position vectors. And using those position vectors, the next step will be to find the displacement vectors. So the displacement vector between 1 and 2, the displacement vector between position 2 and 3, and so forth and so on. Once we have the displacement vectors, we can calculate the average velocity between 2 points, because we know that the average velocity is given by the displacement divided by time, the amount of time between those 2 points. And but here what we're going to do is, since what we're interested in is the direction of the vectors velocity and acceleration, I'm going to ignore the fact that there is a delta t here that I should divide the delta r with, and just replace the displacement vector by average velocity vectors everywhere. So wherever we have displacement vector, we're going to call that average velocity. The difference, as I said, is a scale factor delta t, 1 over delta t, which is not really important and does not affect the geometrical discussion that I'm going to give you here. So with all those average velocity vectors marked all around the circle, we can now proceed to talk about the average acceleration. Average acceleration, as you know, is the change in velocity divided by the change in time. So having those average velocity vectors, we can start thinking about how can we calculate the difference between two of those vectors to give us an idea about the acceleration of the object moving in a circular motion. So at this point, I want to remind you how to find the difference between two vectors. Suppose that you have vectors A and B, whatever directions they are. To find the difference between B and A, that is to find B minus A, what you can do is draw the vectors, redraw the vectors. In this case, we can move, for example, B so that its tail coincides with the tail of A. And then the vector B minus A is the vector that goes from the head of A to the head of B. We know that that should be the case because A plus that red vector should be B, and the only vector that added to A gives you B is obviously B minus A. So using that, we can calculate what is the average acceleration at point 2. The way to do it will be if we knew the velocity, instantaneous velocity at point 3, and we knew the instantaneous velocity at point 1, then we could take the difference between those velocities divided by how much time passed between 1 and 3, and that will give us an idea what's the average acceleration at point 2. Since I don't have those instantaneous velocities, at points 3 and point 1, I'm going to use instead the average velocities that we calculated before, that we have there marked on the diagram. Since delta v13 is velocity at 3 minus velocity at 1, I'm going to replace velocity at 3 with the average velocity between 2 and 3, and I'm going to replace, or use instead of the velocity at 1, I'm going to use the average velocity between 1 and 2. So the vector delta v13 that we're looking for satisfies that vector v, the velocity 1, 2, plus delta v13 should be equal to the velocity v23. So in the diagram, that is the velocity v12, and the velocity v23 is right on top of it, but we can displace that vector so that its tail coincides with the tail of v12. So now v23, after having been displaced, you can see it there in dark green. Now the vector delta v13 that we're looking for satisfies that v12 plus delta v13 should be equal to v23. So v12 is there, plus delta v13 should be equal to v23. So delta v13 is pointing in the direction that you can see in the diagram. Having found the direction of delta v13, now we know what's the direction of the average acceleration vector at point 2, because it is proportional to delta v13. So the acceleration at point 2 points in the direction opposite to the position vector r2. We can do the same, or we can repeat this procedure for the next couple of vectors, v34 and v23, and what we find is obviously that the acceleration vector at point 3 points in the direction opposite to the position vector r3, the same for points 4, 5, and all of them. What this is telling you is that the acceleration is centripetal. I have just given you a way to understand why in circular motion there is an acceleration and the acceleration points towards the center. There is an acceleration because the vector's velocity is continuously changing in time, and that acceleration, as you can see, points towards the center of the circle. This is not a mathematical proof, but in the next segment I'm going to give you a mathematical proof that the acceleration is in fact centripetal, and we'll find its magnitude.